It's 8 a.m. and your chemistry analyzer flags a 1 to 3's violation on the level 2 glucose control. You repeat it, it's still out, you recalibrate, and the next run passes. Case closed, except it isn't because you never asked why the control failed in the first place. Recalibrating and rerunning is a correction. It fixes today's result. Tells you nothing about whether the same failure mode will strike your HbA1c run tomorrow or your creatinine panel next week. Under ISO 15189:2022 and NABL 112, a nonconformity without documented root cause analysis is an open finding waiting to be flagged at your next surveillance audit. Here's what that violation actually looked like on the Levey-Jennings chart. 14 days of stable QC, sitting comfortably within 2 SD, and then day 15 jumps clean past the 3 SD line. That's not noise. A shift or jump like this is the visual signature of a systematic error entering your analytical system. Do the math, and that day 15 point sits at roughly 3.1 standard deviations from the target mean, comfortably past the 1 to 3's rejection threshold Westgard described back in 1981. A single point beyond 3 SD has a probability of occurring by chance alone of under 0.5%, so statistically, something in your testing system genuinely changed. So where do these deviations actually originate? The classic Plebani and Carraro data from stat laboratories found roughly 60 to 70% of total testing errors occur in the pre-analytical phase, but among purely analytical phase errors, the ones your QC is designed to catch, instrument and reagent-related causes dominate. That's exactly the territory a structured root cause analysis needs to search. Skip the root cause step and here's what compounds. The same failure mode resurfaces in a different analyte next month, patient results already released before the flag get quietly questioned, and your NABL assessor stops trusting your CAPA log altogether because a log full of recalibrated QC past entries with no analysis behind them is itself a red flag. So keep this distinction in mind as we go. A corrected QC point tells you the number is fine again. A root cause tells you why it wasn't. And that's the difference between fixing a result and fixing a system. That's the entire premise of this video. We're going to walk through 5Y, the Ishikawa 6M Fishbone FMEA, and the other root cause tools that turn a QC flag into a genuinely closed CAPA, the way your NABL assessor actually wants to see it documented. Let's define our terms precisely, because assessors will test this distinction. CAPA stands for corrective and preventive action, but note it is two separate concepts bolted together, not one. A corrective action eliminates the cause of an existing nonconformity. A preventive action eliminates the cause of a potential one that hasn't happened yet. ISO 15189:2022 clause 8.5 lays out the sequence. Identify the nonconformity, contain it with an immediate correction, investigate to find the root cause, plan and implement a corrective action, verify that the action actually worked, and only then close the record with preventive action rolled out wherever the same root cause could apply elsewhere. Watch how these three terms play out on the exact same event. Correction. Rerun the sample, result released. Corrective action. Identify the reagent lot as the cause and switch it after verification. Preventive action. Build lot-to-lot verification into the SOP for every analyte, not just the one that failed. In plain language, ISO 15189:2022 is explicit that a laboratory must not just correct nonconforming work. It must evaluate the need for action to eliminate the cause, so the nonconformity doesn't recur. That single clause is the entire justification for everything in this video. This is where most labs quietly fail their own quality system. Recalibrating, rerunning, or accepting a repeat pass is not a corrective action. It's correction, and correction alone leaves the door open for the exact same nonconformity next month. NABL 112 layers practical expectations on top of ISO 15189. A defined turnaround time to open a CAPA, a named responsible owner, a documented root cause method, not just a one-line guess, and a monitoring period before you're allowed to call the record closed. When assessors reject a CAPA record, it's rarely because the corrective action was wrong. It's because the paperwork can't defend it. The three most common gaps: a root cause written as human error with no further digging, no evidence the fix was actually verified, and no consideration of where else the same cause could be hiding. So before you write a single root cause, remember this: NABL isn't grading whether you found a cause. It's grading whether you found the cause with evidence and proved your fix actually holds. Let's start with the simplest, fastest tool in the RCA toolkit, 5Y. Developed within the Toyota production system, It's built on one deceptively simple idea: ask why repeatedly, typically 5 times, until you stop hitting symptoms and start hitting a genuine system-level cause. The method itself has 5 disciplined steps. State the problem precisely with data, not impressions. Ask why it happened and write down the answer with evidence behind it, not a guess. Repeat that questioning against each new answer. Stop only when the answer is a process or system gap, not a person. Then verify the chain by testing whether removing that cause actually removes the problem. Here's a real chain from a potassium QC failure. Why did the K+ control flag 1 to 3s? The analyzer's clot detection sensor triggered. Why did it trigger? The sample cup was underfilled below the minimum aspiration volume. Why underfilled? A new phlebotomy trainee used the wrong draw tube. Why the wrong tube? There was no standardized visual checklist at the phlebotomy bench for new staff, and that's your system-level root cause. Before you even start asking why, read the Levey-Jennings pattern itself. It tells you which chain to pursue. A single isolated spike with an otherwise stable baseline points you toward a one-off random event. A bubble, a clot, an operator slip. A shift that persists across multiple runs points you away from 5Y and toward the fishbone, because a persistent shift usually has more than one contributing factor. That distinction maps directly onto Westgard's rule notation. 1 to 3's flags a single point beyond 3SD, your classic random error rule. 2 to 2's flags 2 consecutive points beyond 2SD on the same side, a systematic error rule. Our 4's flags a range of 4SD between duplicate controls, also random. Knowing which rule fired tells you what kind of root cause you're hunting for before you write a single Y. The single most common way 5Y goes wrong on the bench. Stopping at Y2 or 3 right at the operator made a mistake, and closing the CAPA there. That's a symptom, not a root cause. If your final answer has a person's name attached instead of a process gap, you haven't finished the analysis. So build that tool selection logic into your CAPA SOP as an actual decision point. Single analyte, single run, isolated flag with a plausible operator or sample explanation. Run 5Y, recurring flag, multiple analytes, or a shift that survives recalibration. That's your cue to escalate straight to a fishbone session with a multidisciplinary team. Anchor the method with this before you move on. 5. Don't stop early. Write every answer down with evidence. Halt only at a process or system gap. Then verify by testing removal of the cause. That's your 5Y discipline in one line. If your root cause has a person's name attached to it, you haven't found the root cause yet. You've found where the system let that person down. When the problem is recurring, cross-analyte, or survives a first corrective attempt, you need a tool built for multiple simultaneous causes, the Ishikawa diagram, more commonly called the fishbone. Keiru Ishikawa developed it for manufacturing quality control in the 1960s. Clinical laboratories adopted it almost unchanged, because an analyzer's error sources map onto the exact same categories. The classic manufacturing 4M man, machine, material method expands to 6M in the laboratory by adding measurement and Mother Nature or environment. Every one of your analyzer's failure modes lives inside one of these 6 buckets, and forcing your brainstorm through all 6 is what stops you from fixating on the first plausible cause you find. Now put a real problem at the head of the fish. A persistent positive bias on the Jaffe creatinine method, roughly plus 0.3 milligrams per deciliter, sustained across both QC levels for 2 consecutive runs. Brainstorm every plausible cause under each of the 6 bones before you commit to 1, lamp aging under machine, a new reagent lot under material, a rate versus endpoint protocol change under method, an extended calibration verification interval under measurement, a new analyst skipping the QC review step under man, and a lab air conditioning failure raising reaction temperature under environment. Run the session properly and it looks like this. Pull in the analyst, the biomedical engineer, and the quality manager together, not just one person guessing alone. Brainstorm without editing ideas in real time. Force every branch through all 6 categories, even if some feel like a stretch. Push 2 or 3 levels deep on each branch instead of stopping at the first answer. Then rank the branches by plausibility and evidence before you test anything. Notice how the Westgard rule pattern from earlier now points you toward specific M categories. A persistent shift like 2 to 2's usually traces back to material or measurement, a new reagent lot, a calibration drift. Wide random scatter and our 4's pattern tends to trace back to man or machine technique variability, a failing component. That link between statistical pattern and physical cause is what makes your Fishbone brainstorm efficient instead of scattershot. Keep a quick reference version of this pinned at the bench because in the middle of an audit or a night shift, nobody wants to brainstorm 6 categories from scratch. A one-line prompt per M is often enough to jog the right memory. One more distinction to nail before you brainstorm. Random error scatters QC points unpredictably around the mean with imprecision as the main problem, while systematic error shifts the whole distribution in one direction. Accuracy, not precision, is what's broken. Your 6M search strategy differs depending on which one you're facing. So when a resident on the QC roster asks, "Which tool do I use?" here's the actual decision. Isolated random flag with an obvious explanation on review. 5Y closes it in 20 minutes. Recurring or systematic bias with no obvious single cause. That needs the full Fishbone session with a team. Trying to 5Y your way through a genuinely multi-factor problem just produces a shallow, wrong answer. Remember the difference this way. 5Y finds one path down to a root. Fishbone maps out every path worth checking before you commit to one. Quick pause. If this breakdown is helping you, take a second to hit like and subscribe. It genuinely takes a lot of effort to make videos like this, and your support keeps them coming. Pull 12 months of your CAPA log and sort nonconformities by category, and a pattern emerges almost every time. In a typical biochemistry section, reagent and lot-related causes dominate, calibration issues come second, and pre-analytical or sample-related causes round out the top 3, the classic Pareto 80 or 20-foot concentration, where a handful of categories drive most of your findings. When a failure mode is high stakes but hasn't happened yet, say, a new automated middleware rule that could silently auto-verify a critical potassium result, you move from reactive RCA to proactive FMEA. Failure modes and effects analysis walks the same territory before the failure occurs. List every plausible failure mode, score its severity, score how often it's likely to occur, score how likely you are to detect it before harm, then multiply the 3 into a single risk priority number. Worked out on paper, 3 candidate failure modes on your automated potassium pathway might score like this. Reagent probe clogging scores moderate on all 3 factors. A barcode misread scores low severity but happens often. Middleware auto-verifying a hemolyzed sample scores catastrophic severity even though it's rare. And that risk priority number is exactly why hemolysis index auto-flagging deserves your CAPA attention first, ahead of the more frequent but lower stakes probe issue. None of these tools is universally best. They trade speed for depth. 5Y is fast and needs almost no resources, but it can miss multi-factor problems if you stop the chain too early. Fishbone is thorough and built for team input, but it takes real time to run properly. FMEA is proactive and quantifies risk before failure, but building the scoring table itself takes real effort up front. Here's a lens most people never apply to QC rules. Think of the Westgard multirule set itself as a screening test for analytical error. Westgard's own validation work showed the combined 1 to 3s or 2 to 2s or R4s or 4 to 1s or 10x rule set catches the great majority of true systematic and random errors, while keeping the false rejection rate, flagging a control that's actually fine, down around 1 to 2%. That's your rule set's own sensitivity and specificity. If your Fishbone points toward the reagent lot as the likely culprit, don't just assert it, plot it. Chart QC bias magnitude against days since the reagent bottle was opened across several lots, and a rising trend line is objective evidence of reagent degradation, not a hunch. This single chart can be the difference piece of evidence your CAPA record needs. The literature backs the structured approach with real outcome data. Laboratories that formalize root cause analysis into their quality system consistently report fewer repeat nonconformities on subsequent audits than laboratories that document correction alone. It's not just good audit theater. Structured RCA measurably reduces recurrence. Match the tool to the failure's complexity, not to whichever one you're most comfortable reaching for. A 5-minute problem doesn't need an FMEA table, and a genuinely multi-factor problem will never survive being squeezed into a 5Y chain. Let's run the full workflow on one real event, start to finish. Both creatinine QC levels drift positive by roughly 0.3 milligrams per deciliter and hold there across 2 consecutive runs. The Westgard 2 to 2s rule fires, flagging a systematic, not random, error. Here's how the timeline actually unfolded on the floor. Day 0. The flag fires and the run is held. An immediate correction. Day 0, same shift. 5Y is run and stalls at new reagent lot, which is too broad to act on. Day 1. The team escalates to a full 6M Fishbone session. Day 2. The reagent lot branch is confirmed with side-by-side testing. Day 5. The corrective action goes live. Day 35. Effectiveness verification closes the record. The decision path the team actually walked. Random or systematic. The 2-to-2s pattern says systematic. Reagent, calibrator, or instrument. Side-by-side testing of the old versus new lot on the same calibrator and instrument isolated the reagent lot as the variable that moved the bias. Everything else stayed constant. Before the corrective action, mean bias sat at plus 0.3 milligrams per deciliter with a coefficient of variation pushed outside the desirable limit from the RICOS biological variation database. After lot re-verification, bias returned to essentially zero and CV settled back within the desirable specification. Objective numeric proof the fix actually worked. For the final objective proof, run a method comparison between the old and new reagent lot across the actual clinical range of patient creatinine values. Plot the mean of each paired result against the difference, and if your points cluster tightly around zero with narrow 95% limits of agreement, you have quantitative, defensible evidence that the corrective action closed the gap, exactly the kind of data an assessor wants attached to the closure. For anyone setting this up on their own bench, the lot verification protocol itself has 4 concrete steps. Run both lots against the same calibrator on the same instrument. Split 20 patient samples spanning the clinical range across both lots. Calculate the mean bias between lots at each concentration. Compare that bias against your laboratory's allowable total error before accepting the new lot into routine use. After the fix, residual bias measured just 0.02 milligrams per deciliter against a laboratory allowable total error of 0.3 for creatinine at this concentration, comfortably inside spec, and the number that ultimately justified signing off the CAPA as effective. 6 months of monitoring later, the number that matters most on this record: 0. 0 recurrences of the same bias pattern on creatinine, and 0 related findings when the reagent lot verification SOP was cross-checked against the other analytes it now covers. That's the full loop, and it's worth repeating. A root cause isn't confirmed the moment you identify it. It's confirmed the moment you prove that removing it removes the problem, with numbers attached. Every complete CAPA record needs 8 elements sitting in the file together, not scattered across separate documents. The problem statement with data, the RCA method used, the confirmed root cause, the corrective action taken, a named responsible person, an implementation timeline, documented effectiveness verification, and final sign-off approval. Timeline discipline matters just as much as content. Map the RCA session, SOP revision, staff retraining, and the effectiveness monitoring window onto an actual project timeline. Assessors specifically look for whether your monitoring period was long enough to genuinely catch a recurrence, not just long enough to look compliant on paper. Think of every CAPA record as moving through the same 7 stages regardless of which analyte or instrument is involved. Identification, immediate correction, root cause analysis, corrective action, effectiveness verification, closure, and finally a preventive action rollout to wherever else the same cause could apply. Skipping straight from correction to closure is the single most common shortcut assessors catch. One closure myth deserves a direct correction. Implementing the corrective action is not the finish line. ISO 15189 and NABL both expect documented evidence, collected over a defined monitoring period, before you're entitled to mark the record closed. Quality indicator literature consistently shows the same pattern. Laboratories that build a monitoring period into every CAPA closure catch meaningfully more premature closures. Cases where the fix looked good on day 1 but the cause resurfaced within the following quarter, than laboratories that close on implementation alone. Look at what a genuinely revised SOP looks like against the vague version it replaces. The old wording just says, verify new reagent lots before use. No defined method. No acceptance criterion. The revised wording specifies the exact comparison protocol, the sample size, and the numeric bias limit against allowable total error. Before your next NABL surveillance visit, run this 5-point self-check against your own open and recently closed CAPA files. Is every root cause written as a process, not a person? Is the RCA method actually named? Is effectiveness data attached, not just asserted? Was the same cause checked across other analytes? And is there a named, dated sign-off? Keep this as your final filter on every record you sign. An unverified corrective action is just a hypothesis with a signature on it. Step back from any single case and the real point of this whole system comes into focus. Every QC flag your analyzer throws is a question your laboratory is being asked. 5 Fishbone, and FMEA aren't paperwork. They're how you make sure you actually answer it instead of just making the flag go away. Quick check before we close out. Your K plus level 1 QC shows a 1 to 2's warning on Monday, then a confirmed 1 to 3's violation on the same level Tuesday. What does that pattern most strongly suggest? Carry these 4 numbers with you back to the bench. 5 as your minimum Y chain depth, 6 as your fishbone categories, 1 as the named owner every CAPA needs, and 100% as the verification standard NABL actually expects before closure. So here's your action plan for the next QC flag that hits your bench. Read the Levey-Jennings pattern first. Match the tool to the complexity, 5Y for isolated flags, Fishbone for recurring ones. Gather objective evidence, don't just assert a cause. Verify the fix numerically before you close. Document all 8 elements in one complete record. One last memory anchor before you go. Random error means scatter and imprecision, so think man or machine first. Systematic error means a shifted mean and inaccuracy, so think material or measurement first. And for the 6 fishbone categories themselves, here's a line worth keeping in your head every time a nonconformity opens. Man, machine, material, method, measurement, and Mother Nature, the environment. Every root cause on your bench lives in one of those 6 houses. Every QC flag is a question. 5Y and the fishbone are simply how you make absolutely sure you've answered it, with evidence, not just a signature. Here are the key references and sources for this video. Thanks so much for watching. If this helped, like the video and subscribe for more clear, simple explainers, and I'll see you in the next one.